Carbon dioxide passes point A in a 3-inch pipe at a velocity of 15 feet per second. The pressure at position A is 30 psig, and the temperature is 70 degrees Fahrenheit. Then downstream at point B, the pressure is 20 psig and the temperature is 90 degrees Fahrenheit. If the barometric reading of the atmosphere is 14.7 psi, we want to calculate the velocity, linear velocity of the air at position B, and also compare the volumetric flow rates at both positions A and B. So the first thing to note is that this is a gas flow problem. That means the gas is a compressible fluid. We cannot assume it's an incompressible fluid. We're also going to assume that CO2 is an ideal gas. This is going to make things much easier for us. We also need to note that the pressure is given to us in psig, in gauge pressure. And remember, when we do gas problems with ideal gas law, we are going to have to use absolute pressure. Now, I'm not going to draw a schematic. It would be nice to be able to easily draw a schematic, but in this we can just simply assemble our information for position A upstream and position B downstream. And so remember, at position A we've got a 3-inch diameter pipe. And is the diameter going to stay constant? We're not told anything, so we're going to assume the diameter stays constant. So we'll just say D is equal to 3 inches. And again, this is inner diameter. The velocity, linear velocity at position A is 15 feet per second. The pressure at A, remember this needs to be absolute pressure, so I'm going to change to absolute pressure, is 30 plus whatever our atmospheric pressure is. So that's 44.7 psi. And then our temperature, because we're dealing with the ideal gas law, we need to have things in absolute temperature. I went ahead and converted the 70 degrees Fahrenheit to Celsius and then converted that to Kelvin. Now at position B, we do not know the velocity, so that is going to be one of the things we're going to need to find. We do know the pressure. It's at a lower pressure, which we would expect for something going downstream and having no compressor or fan in between. And then the temperature is a little bit higher. All right, the temperature is a little bit higher, and so I again have converted that Fahrenheit temperature to Kelvin. Another thing that I input is the molecular weight of CO2, because we are going to probably need to use a continuity equation, and so if we need to convert molar density to mass density, we need the molecular weight and we need the ideal gas law constant. So the first thing that I would do is write the continuity equation, because even though the gas is incompressible, we have conservation of mass. So the continuity equation still applies. We have rho VA at position A is equal to rho V times A at position B. All right. Now the nice thing about this problem is that the pipe diameter is constant. So the area terms are going to cancel out. All right. The area terms are going to cancel out. Notice that since gas is compressible, we cannot cancel out the density. Right. The density is changing. And so what we're left with the continuity equation is rho A times VA is equal to rho B times VB. And what do we need? We know, can we calculate rho A? We know pressure and temperature. So if you think ahead to the ideal gas law, yes, we can calculate the molar density and then convert that to mass density with our molecular weight. We know VA, we know pressure and temperature at position B. So we can get the mass density at position B, and we're left with just V sub B, the velocity that we're asked to calculate. Notice that they also want us to know what the volumetric flow rates are. And remember, what are the volumetric flow rates? Volumetric flow rate is simply equal to the linear velocity times the cross-sectional area. And so once we know the linear velocity at position B, we can certainly calculate the volumetric flow rates at both of these positions. So the first thing we will do is we will calculate the molar density, and then we will convert that to mass density. And so I've done that here. The ideal gas law says PV equals nRT. So the molar density is equal to N over V, which is equal to P over RT. And so we do that for position A and for position B. And so at position A, we get a molar density of 125.98 moles per meter cubed. We multiply that by the molecular weight, and we get a mass density of the CO2 at position A. We go through the same process at position B. We get a molar density at position B. Notice it's a little bit lower. We get a mass density at position B of 4.147. Now what we can do is we can plug in and we can solve for the volume at position B. So we take our continuity equation, we simplify and solve for the velocity at position B. We get a velocity of 6.1 meters per second, or 20.05 feet per second. And so what was the velocity at position A? It was 15. The velocity increased, right? The velocity increased even though the pipe diameter stayed constant. Remember, if we had had an incompressible fluid with a constant diameter pipe, the velocity would have stayed the same. But the velocity increased because it's a compressible fluid and the conditions have changed from going from position A to position B. So now that we know the velocity at position B, we can then plug it into our velocity and cross-sectional areas into our equation for the volumetric flow rate and calculate the volumetric flow rates at positions A and B. And we do that, so the cross-sectional area pi d squared, that's going to be the same over 4 for each. It's going to be the same for both conditions. We get a volumetric flow rate of 0.736 cubic feet per second at position A, and we get a higher volumetric flow rate of 0.984 cubic feet per second at position B. And again, this is occurring because our volumetric flow rates are different because carbon dioxide is a compressible fluid, right? So this is in contrast to what we have done with incompressible fluids, where the densities would stay constant, and if the mass flow rate of an incompressible fluid, the mass flow rates would be the same for an incompressible fluid, and because the densities are the same, that would mean for a constant diameter pipe that the volumetric flow rates would also be the same. So make sure that you work through these problems step by step to make sure you don't miss any of these things. Gases are compressible. You have to take that into account when you're solving these problems.